It's my pleasure to thank the organizer committee to let me give in this talk in this workshop. My talk entitled Minimum Length Uncertainty Approach to Cosmological Constant Problem, presented by Abdelmekid Diab from Cairo, Egypt, and in collaboration with my professor, Professor Abdel Nasser Tawfiq. The outline of my talk is given as a follow. The first, the introduction includes four parts. I will give short notes about the Einstein field equation and the expansion of the universe, and I define the redshift phenomena and which related to the expansion of the universe. And finally, I would like to define the cosmological constant problem. In the second, I will show the methodology where the main idea should be appeared. In the third, I will show the approach which we are used in this work, generalized uncertainty principle or GOP, and give a possible solution to the cosmological constant problem, and finally to present the conclusion. In the introduction, Einstein field equation. In the first, Einstein field equation describe how mass and momentum create the curvature in space-time. There is by creating the apparent force of gravity. Einstein field equation also describes such phenomena as black hole and gravitational waves, and also the accelerating expansion of the universe. In Einstein field equation, the first and the second term in the left-hand side are known as Einstein tensor, which represents to the curvature of space-time and determined by the metric of geometry. In the right-hand side, where the first term represented to the matter energy contents of space-time. The last term in the right-hand side is known as the cosmological constant. The cosmological constant governing the rate at which the expansion of the universe is accelerating, which operating in opposite the gravity. Einstein field equation also can interpreted by a set of equations showing how matter energy and energy determined in the curvature space-time. The cosmological constant is equivalent to the energy density. In 1917, Einstein introduced the cosmological constant because he believed that the universe is closed static universe. In 1922, Friedman discovered the expansion solution to Einstein field equation in finishing the cosmological constant and defined the three solutions in three forms. Defined related to the density parameter, where the density parameter defined as the ratio of the density of the universe to the critical density of the universe. The three cases are given as a follow. In the first case, where the density parameter is greater than 1, where the universe is closed universe. In this case, the density of the universe is greater than the critical density of the universe. In this case, the gravity stops the expansion of the universe, and after which it starts to contract all matter and collapse to a point where the final singularity. The second case, where the density parameter is lower than 1, where the universe is open universe. In this case, the universe expands forever, where the gravity is slowing the rate of expansion. The third case, where the density parameter is equal to 1, in this case, the universe is flat. In this case, the density of the universe is equal to the critical density of the universe, and the flat universe expanded forever, but at continuous accelerating rate. The third part of our introduction is given as redshift phenomena, which related to the expansion of the universe. From our knowledge of electromagnetic light, the red light have longer wavelengths and the blue light have shorter wavelengths. The red shift and the blue shift describe how light shifted shift toward shorter or longer wavelengths as the object in space, such as stars and the galaxy, move to closer or away from us, which means that when galaxies are moving away from us, we have the light towards to longer wavelengths. We have red light, which means that the galaxy themselves are moving away from us, and the universe will be expanding. This phenomena is related to the expansion of the universe. All of this gave below the static model of Einstein field equation and discarded the cosmological constant. The current interest of cosmological constant stem mainly from observation of type redshift supernova, which indicate that the universe is accelerating with a small cosmological constant term. The fourth part of our introduction is related to cosmological constant problem. We will define what is the cosmological constant problem. We have two estimation value of cosmological constant, one experimentally related to blank 2018 observation, and the second is theoretically estimation value related to quantum field theory. For blank 2018, the cosmological constant is related to the Hubble parameter and the dark energy relation, dark energy density. From this relation and using blank data, we find the observed cosmological constant is equal to in order of magnitude 10 power minus 47. For theoretical estimation value from quantum field theory, the cosmological constant is calculated from the sum over the vacuum fluctuation energy corresponding to all momentum particle states, where by solving this integral we find that the estimation value of quantum field theory cosmological constant is equal to an order of magnitude 10 power positive 74. The large gap between these two values, where the cosmological constant of quantum field theory of estimation value equal to 10 power minus positive to 121 from observed experimental value of cosmological constant. The disagreement is one of problem in physics is known as the cosmological constant problem. The second point of my talk, I will give the main idea of our work, here is the methodology. As we defined it in quantum field theory, the cosmological constant is given from the sum over vacuum fluctuation energy in volume phase space. Here we will use our approach generalized uncertainty principle to modify the number of states in volume phase space. Secondly, and I will modify the dispersion relation in momentum space. By using this approach, we can define a new dispersion relation and a new momentum phase space. This analogy can be found by using the theory of Liouville theorem in the classical limit. But we need to make sure that the size of each quantum mechanical state in volume phase space is depending on the modified momentum. And in other words, the number of quantum states in phase space is assumed to be independent on time. The third point of our talk, I will show the model we are used in our work, which name generalized uncertainty principle, or GUB. GUB is an extended version from Heisenberg uncertainty principle, which have a correction term including the gravitational impacts. From GUB we can find the minimum length uncertainty, which have some advantage in UV and IR corresponding, where UV and IR corresponding is relevant to some problem of short distance physics, such as our problem in this case, the cosmological constant problem. In this slide, I would like to highlight our review of generalized uncertainty principle, which published in a famous journal, reports on progress in physics, which have impact factor about 16 impact factor. This review is well-known review and we give different approaches of GUB, and we show in different application in quantum physics. It's a very well known review, and I shall just to read it. Generalized uncertainty principle. The unification of the classical description of quantum mechanics and general relativity is still an open problem. The two theories can be used as guiding principle to the search of the theory of quantum gravity. Different approaches from theoretical analysis, such as string theory and black hole physics and double special relativity, is the existence of the minimum measurable length. Also, some experiments aim to study the effect of quantum gravity and suggest that the Heisenberg uncertainty principle should be modified to be called the GOP. Approaches to the energy of Planck energy. In string theory, the quadratic GOP with minimum measurable length treat as this equation, where we have a modification in quadratic momentum and beta is the GOP parameter. For UV, ultraviolet, and IR, infrared corresponding, where delta X is proportional to delta B, the variance of delta B, where we, for large delta B in the range of ultraviolet become proportional to the large delta X in infrared range. The GUB, this GUB will modify also the Heisenberg algebra, where we have modification in quadratic momentum with beta parameter, GUB parameter. The GUB parameter is related to the Planck length and the energy of Planck energy. Beta naught is dimensionless parameter. From this quadratic GUB, we can find the minimum length uncertainty of delta X minimum is related to the GUB parameter in order of the Planck length. We will back to the slide of methodology, where the main objective of our work. We will use the GUB in order to modify the theoretical definition of the cosmological constant in quantum field theory. We will modify the number of states in the phase-space volume by using Liouville theorem, and also we will modify the dispersion relation. So we will modify the dispersion relation and the number of states in volume phases. Before we do the modification on number of states in volume phase space and the dispersion relation, we will present an local estimation of the GOP parameter beta naught, which would be useful for solution of cosmological constant problem. Instead of violation the Lorentz invariance, we would investigate the speed of graviton and comparing with the last observation of gravitational waves, GW170817 event. Event GW1708-0817 was the gravitational wave signal observed by LIGO and Virgo detector, where the signal was produced from the merging of binary neutron star. So that instead of violation Lorentz invariance, we will investigate the speed of graviton from quadratic GUB. We will have the modified term in order of beta parameter, GUB parameter. When beta tends to 0, we will have the standard speed of graviton as a function of the energy of graviton. It's very useful to find the difference between the speed of light and the speed of graviton, where C minus graviton speed will have this term in the limit of massless particle of graviton. The variance or the difference between the speed of light and the graviton are given in order 10 power minus 18 beta naught in units of speed of light. The upper bound of the dimensionless parameter beta naught of quadratic GOP is given in order of magnitude 10 power positive 16. This improved upper bound value is very similar to the ones reported to previous works related to cosmological observation. This value is very useful in our presentation for giving a possible solution of for cosmological constant problem. In the current slide, we will give the main key of our work, where the possible solution of cosmological constant in the present of GOP model. In this presentation, I will present the theoretical definition of cosmological constant in quantum field theory in the present of the GOP from the Liouville theorem in classical limit. And by using the GOP model, we'll have the weight factor in 3 dimensions in this equation as a function of beta GOP parameter. From theoretical definition of quantum of cosmological constant, we have the summation over all momentum fluctuation energy corresponding to the momentum states, and this integral is an infinite integral. But it usually we can cut off at the blank scale from 0 to blank length. We will find this value of cosmological constant or the vacuum energy density in the limit of massless particle of graviton, where the cosmological constant is given in order of blank mass or blank energy, mb c square over 2, and also in order of dimensionless beta parameter of quadratic GOP by using the value of blank energy and the estimation value of beta naught from the comparison with GW 170817 observation of gravitational wave event. We will find the limit of the cosmological constant is given in order of 10 power minus 48. So our conclusion of the current work, the main conclusion of our work, the cosmological constant problem, where the theoretical value of the cosmological constant is equal to 121 times from observed quantity from blank 2018 observation. But in our presentation about the possible solution of cosmological constant problem, we will have the estimation value of cosmological problem of cosmological constant in the present of GOP is equal to 0.1 from the observed value from blank 2018. We think that the possible matching between the estimation of our bound GOP parameter from gravitational waves, last gravitational waves observation GW 170817 event could be solve the large gap between the theoretical and experimental estimation of blank estimation value of cosmological constant. All of this could be support the great importance of constructing the theory of gravity. And finally, thanks for attention.